Okay, how's everyone doing today? We're here, right? Okay. This is Wednesday, so it's the end of whatever week it is. We have two more sections to take a look at, one today, one on Monday, and then we will have everything under our belt for the next exam. We'll have a review next Wednesday, and there's this 12.6 elasticity that will not be on the test. In the past it has. This time they're not putting it on the test. So I'm going to count it as extra credit. You can either choose to get to it. There's a recorded lesson in there that you can watch. It's not too bad if you walk your way through it, but it's also something you could do later in the semester. Okay, so I've got it. If I haven't, let me know, but I've moved that due date way to the end, so you can do it whenever you want. Okay, I will start updating the grades in it, but since it's extra credit, it counts for 0, so unless you actually do it, it will add that extra credit in whenever you have it done. Until you do, having a 0 on it won't hurt you because it doesn't get factored in any other way. Also, I want you to start thinking about the review materials for Test 2. It's not too soon to start maybe taking a look at them. I've updated. There's a brief study guide that gives you an overview of all the topics we have talked about. And then we've got the most current one that does list, it's got the questions from 12.6, but it lists them as optional because it won't be on the test. Okay. What I'm going to do this time for the test review, the 50 points, instead of just working through, I still want you to work through this. I'm going to come up with a 4 or 5 question quiz that will be online. You can do it through Canvas. As long as you do it enough, you'll be able to see it. And I will take it from the previous exams, the open question type exams. It will have those open questions. There will be some multiple choices for it, but there will be also a place to kind of where you should show your work. Once you submit, you'll see the answer. You'll see what the work looks like, or at least what an example looks like. So what I'm hoping is that you get a feel for the types of questions that would be in that open response area, and maybe how to address them, how to go forward with them. No, not this Monday. A week from Monday. So we've got today. Monday we're going to look at 12.5, and then we've got a week. On Wednesday we've got the review, and the following Monday we have the test. Today's 12.3. 12.3. So we're going to talk about the second derivative today. So let's go ahead and get into that. Okay. Further applications. So higher order derivatives. We're going to talk about acceleration and concavity. Now, a second derivative, all you have to do is you take the derivative once and then you take the derivative again. So the techniques for taking that second derivative, there's nothing new. It's just you've got to do it twice. So you take a derivative and then you apply the same rules on this as if it were a new function. But the meaning of what we're getting, remember, what's the meaning of a derivative? What does the derivative give us? Rate of change of a certain time. So the original function maybe gives us some kind of a value, like it gives us the profit. The derivative of the profit function gives us how the profit is changing. Right? Sometimes we could refer to that as the marginal profit at a given place. So it's how the profit's changing. So what would the second derivative be? It would be the rate of change of the rate of change. So it's either how quickly we're changing, or maybe the change is slowing down. So that second derivative is a rate of a rate. So one of the best ways to figure out what that is to think about acceleration. So when you're in a car, your velocity, that first derivative, is your speed. That's how your distance is changing. That's your speed. The second derivative is your acceleration. Are you speeding up or are you slowing down? Right? So it's not that you're going 55 miles an hour, it's that you're going 55 and you put the foot down, then your second derivative becomes positive, you're picking up speed. You put on the brake, your second derivative becomes negative because you're slowing down. So that's what we're going to get from the second derivative. Okay. So we'll talk about acceleration. So that's the physical description is we've got a function that gives us where our position is, how our position is changing over time. And the average rate of change, or certainly the instantaneous rate of change, would be our speed at any given time. The second derivative is how our speed is changing, whether we're speeding up or slowing down. So that is acceleration. Okay, so, excuse me. I've got to get this thing turned on. And I'll just say, you guys must have had some really good energy. I've had this, I've got an infected tooth. I have to go get a root canal done. And I've had this killer headache for the last 5 days. I entered this room and now it's like my headache's gone. I go, oh, this is cool. I haven't felt this good in a while. So hopefully I'm making sense. I don't know, or the ibuprofen's kicking in. I don't know, one of the two. But so what we have, let me, I guess, back up, is that S of t is some kind of a position function. So it's how our position is changing over time. And we could basically, if we plug in something, what the value we get is distance, how much distance was traveled. So I drove for 2 hours. Position function will tell me how many miles I covered, right? If I take the derivative of that function, I get its velocity, I get the speed that happened in, right? It's a rate, it's distance, miles per hour, some kind of thing like that. So that's the velocity. And when I take the derivative of velocity, I get something called acceleration. So velocity comes from the derivative of the position function, and then when I take the derivative of the velocity function, I get something called acceleration. So acceleration is going to be thought of as the second derivative of the position function. Okay, and so we use two little primes. You'll see the notation here to just mean I'm taking the derivative of the derivative. So we start with position. We take two derivatives. We've got acceleration. The middle derivative is our speed. Does that kind of make sense? Okay. And again, the best way really to understand calculus is to go on a roller coaster ride. You get the feel for acceleration, for velocity, and how things change. Okay, so the acceleration function is a derivative velocity function, which is a derivative of the position function. So second derivative. Okay. What would the third derivative be? Again, we lose, I don't know, how the acceleration's changing. But those are basically the three things we get to understand derivatives. Because we could actually, with some functions, we could take an infinite number of derivatives. We could take the 100th derivative with some types of functions, but we'll only go to two derivatives. Okay, so you're going to see some word problems that involve position, velocity, and acceleration. And a lot of times they'll just give you the position function and they'll ask for the acceleration. You're just going to have to remember, to get to acceleration, you've got to take two derivatives. They may not ask anything about the velocity function. We'll look at a couple examples in here and see how that works. Okay. So here's a quick example. So if we've gotten a function x to the third minus x. We take its first derivative, right? The 3 comes down, subtract 1 from the exponent, we've got 3x squared. Derivative of negative x is just negative 1. And then if we take the derivative of this middle part, which is the second derivative, the 2 comes down, 2 times 3 is 6, subtract 1, that the second derivative would simply be 6x. Okay, so notice how the skill level stuff that we're doing with taking derivative is nothing new. It's just once you take one derivative, you treat that function as a new function, take its derivative, and we've got this. So if this first function, f of x that they gave us, if that was a position function, this middle derivative, the first derivative would be velocity, speed. I like to just call it speed. I understand speed a little bit better. This is acceleration. So again, this is whether I'm speeding up or slowing down. Because actually braking is acceleration as well. It's just negative acceleration. Okay. And then we can plug those in. So, and again, another example here using specifically s of t for position. I don't know why s. It must. Sometimes these are done in different languages, maybe in German or something, and the German word for distance or position is s. I don't know. But they'll use s oftentimes for the position function, v for velocity for the speed function. And again, velocity is the first derivative. And then when we take the second derivative, just taking the second derivative, that's the first derivative of velocity, the second derivative of position. Okay. And again, we'll look at, this is from the homework. You'll have some different numbers, but let's just kind of walk through how you would go about doing this. So they give you a position function s at some point. Here it is. They're going to give us that they want it at t equals 4. But they want the point's acceleration as a function of t. That simply means take its second derivative, right? But you can't just jump to the second derivative unless you're incredibly brilliant and can do it all in your head, which I'm not. So we take the first derivative. Position is going, the derivative of negative 12 is 0. Derivative of t is 1. So the derivative of t is 1, and then derivative of negative 18t squared is going to be negative 18 times 2 is 36 t. So that is our first derivative, which would be velocity, right? It's not acceleration yet, that's our speed. That's the first derivative. To get to acceleration, we need the second derivative. So take the derivative of the derivative. Derivative of 1 is 0. Derivative of negative 36t, just negative 36. It's a constant, so our acceleration is constant. It's negative, which means what? We're slowing down. Okay. As a function of t, it's negative 36. So find the point's acceleration at a specific time. Well, if we plug 4 into this function, there's no place to plug anything, right? It's the constant function. It's always negative 36. Now again, we need to have some domain on this, because if you're slowing down, can you slow down forever? Eventually you're going to stop, right? I guess, or you start going backwards. I guess you could do that. But somewhere along the lines we would probably get there. But this is also, we'll see this come into effect like with falling things, yes?
So does acceleration always equal the second derivative of velocity?
It is, it's a second derivative of the position. It's the first derivative of velocity, because velocity is the first derivative of position. It can get more confusing than it needs to, but there's position, velocity, acceleration. Okay. So it's the second derivative of the position function. And then the homework, that's what they'll give you. They'll give you the position function to start with. So just kind of get, yeah, I've got the s. They gave us the velocity function, then we'd only need one derivative. Okay. So far, is that okay? So yeah, most of this, it's not going to be the technique of taking a derivative that's going to do it. It's just going to be understanding what are they looking for, right? And there's a few different ones. They give you different functions that they start with, but they're all pretty much the same. They're giving you a position function, and they want to get to the acceleration function. Sure, sure. So you're saying if this was negative 36t squared? Oh. Right. Yeah. If this ended up with a variable, this is where we would write it. So this was like negative 36t. We'd write that. It's just because it was a second derivative, it ends up just being a constant. Yeah. But I'll show you. Let's do a quick example. So far, because I know it's kind of doesn't. So if our position function were something like, let's just make it t to the fourth, right? So then our velocity, the first derivative, is going to be 4t to the third, right? We subtract 1. And then the second derivative, or the acceleration function, is going to be now 12t squared, and that would be what we put in. We would put that in the box, and then down here we would find s of 4 equals 12 times 4 squared. Then we would plug it in. Yeah. So they just gave us a function that and this happens sometimes, by the time we get to that acceleration function, there's no variable left. And sometimes, had it been a linear function for the position function, by velocity you're constant, and by acceleration you've got zero acceleration. It just means you're not speeding up or slowing down. So it is also possible for this acceleration function to be 0, which doesn't mean there's nothing to plug in, and you're always going to have 0. And it just means you got, yeah, the lawnmower's on autopilot, and it's not going to slow down or speed up until it hits something, I guess, But yeah, does that help? Yeah, but yeah, it's so, and because the last exam there was a question like this where find it in reference to t. Some of you went ahead and just put the function. Some of you were looking to make it into a number, and that's not what they want. They just want that derivative, whatever it is. Okay. So this is just some notation that comes up, and you don't have to really know too much about it, except that when you see something like this, what is that? It's the second derivative, okay? And they kind of give an example down here that you're taking the derivative of the derivative, and so the notation, since it's d of x, it's just d squared f over dx squared. You're just going to see in the homework they will ask the question that way. You see the 2, to take the second derivative. You won't have to generate that formula or this on your own. Because when I do it, where does that 2 go? Does it go on the f or does it go on the d? Which one does it go on? It's not important. Just know that when you see something like this, it came from df dx or dy dx, that it's the second derivative. And I think I've got an example that's going to come up. So you just need to be able to see that when they ask for this and they give you this, that you're going to be taking the derivative 2 times. And again, they jump the boat, just go to there, but what's the derivative? Well, I like to use this prime. The first derivative would be 3x squared, and then the derivative of the derivative, which is the second derivative, 2 times 3 is 6. subtract 1 is just x. So that's how they got there. But they make it look like they did it in one step, but you always have to take those two steps. You have to take the derivative first, derivative of the derivative. At least I always do. Again, some of you may see the patterns and you'll be able to jump the boat and say, okay, just do this, and you're doing part of it in your head, that's fine, but that's all it is. Okay, so just be aware of that notation. Again, you won't have to generate that notation, because when you're working through things, you can use any notation you want. I just lean towards using that prime. The second means that two derivatives. Okay. So this is like in the homework. They'll give you something. They'll ask you this question. You just need to know, what are they asking for here? The second derivative. So they just give us a function. And be careful. I've seen a few people and had questions about things like this. Let's first rewrite this. A negative here for x to the minus 2. Because I think some people, I know I used to do this, try to look at that 2 and say, okay, I'm going to subtract, but I know it goes the other way, so I'll put a 3 down there, but I'll miss up on the negatives. So take the extra step of moving that x squared up to the main line and make it a negative 2, so that when you take that first derivative, you know that the negative comes down, so you've got a negative times a negative. Negative 2 times negative 4 is going to give you a positive 8. You're going to subtract 1, so that's going to become x to the minus 3. Leave it this way, because now we're going to take the derivative of the derivative, so derivative of the derivative, negative 3 times 8, negative 24. And then I subtract 1, so notice it feels like the exponent is getting bigger, but it's becoming more negative, which is smaller. But so try it that way instead of trying to maybe save a step and not move it up, and because it's going in a different direction, right? You can at the end if you want, and then again, be careful with this. I've seen people, they'll move the x to the negative 4th down, so that's x to the 4th, but they oftentimes, you'll move the 24 down with it because you think it's attached, but the 24 stays up in the numerator, so that's negative 24 over 4. And again, the WebAssign probably will accept this as an answer too. When we get to the test, if it's multiple choice, just be able to recognize both of those. If it's open answer, I'll accept either one. They're both correct. Okay, so again, nothing new. It's just that we have this extra step. Take the derivative first, and then the derivative of the derivative. Clear so far? Nothing? Okay. Acceleration due to gravity, you kind of see this last one. So we have a position function, and this always, anything that's gone up and then, what goes up comes back down. The reason it comes back down is because of the gravity, and gravity has a particular pull. Pretty much, it's a little different, I guess, at the top of a mountain than at the bottom of the ocean, but not much. So there is this constant, so you'll see this in feet per second, the pull of gravity. So you'll typically see this negative 16x squared as the factor of gravity. Okay, so whatever the starting is, if you just drop something, gravity pulls it down. Sometimes there'll be an extra term if you take a ball and you throw it up. That power that you throw it up gets it going up first, and then it comes back down. The gravity will take over. If you throw it downwards, you've got that. But what you see is that the first derivative is going to give you the speed of whatever it is that's dropping. Notice it doesn't matter where you start, because this s naught, that's the height it started at. That you take that derivative, that's 0. Derivative of negative 16t squared is going to be negative 32t. So as time goes on, this falling object speeds up, but its acceleration actually is constant, because if we take the second derivative, well, that's going to be the next page, but I'll jump the gun a little bit. If we take the second derivative, we get just negative 32. Just like we did in that last one, acceleration's a constant. Okay, it's speeding up, but it's speeding up by 32 feet per second. So it's getting faster. The negative means it's falling. The position's coming downwards. So and again, here they got the acceleration is a second derivative, it's a constant. So the effect of gravity, once everything's settled out, is going to be negative 32 feet per second is how it speeds up. Any skydivers in here? Oh, not you, but okay.
What's the second, like why is the second squared?
Oh, because this is a rate of a rate, right? So velocity or speed would be feet per second. And then when we take the derivative of that, that's another rate, that's seconds per second. So acceleration has units of feet per second, which I still to this day don't really understand it, so I'm not going to try to pretend I do. Maybe the physics professor can explain that. It's just speed's getting faster or slower, but it's second per second. I try not to think about it too much. It just, okay, that's what that is. We experience it like we're in a car. We know when we're speeding up or slowing down. That feel that we get, that's what that rate is doing. But at an abstract level of what units are really involved, I get lost. But I just look for that. Then when you see something like miles per hour squared, you know they're talking about acceleration. That's kind of, so it's kind of an intellectual thing that we do, but no. All right, so far so good. Okay, so the second derivative, the physical explanation of it, if it's position, first derivative is speed, and velocity is just directional speed, so up or down, whatever. And then the second derivative becomes acceleration. Okay. And when we're talking about an object going up in the air, that 32 feet per second is the acceleration due to gravity. So we all fall with the same acceleration, doesn't matter, but we also have air resistance, so you'll see those like skydivers kind of make themselves big. That will slow them down because of air resistance. You could speed up when you fall, but make yourself into a ball. That's air resistance, but the effect of gravity is the same all the way down. Okay, got plenty of time. Now we're going to look at what the second derivative gives us as far as what it looks like on a graph. Okay, it will describe what's happening with the graph. So which one of these functions, f of x or g of x, is increasing? Which one? F of x is increasing. How about g of x? That's a trick question. They're both increasing. Yeah, so if you think, it looks like they're both increasing. They're both going up from left to right. So they are both increasing, but they're increasing differently. Which one's getting faster? F of x is, because it's getting steeper. So that's increasing at an increasing rate. So this is where the second derivative comes in. We're seeing they're both increasing, so they would both have a positive first derivative. Their first derivative will both be positive. This one is going to have a positive second derivative because it's getting faster. This one is getting slower. They're putting on the brakes. Okay, so this is going to have a negative second derivative. Both will have a positive first derivative all along these curves. This will have a positive second derivative, a negative second derivative. Okay, and the way I remember that is If you look at this, if you were to look at sort of it in its entirety, anything like this, we call it concave up, and just focusing on this, the second derivative is always going to be positive. And when something positive happens to you, what do? You smile. Okay, so maybe I'm crazy, but this will always have a positive second derivative. So the second derivative of f of x, in this area at least, will be positive. Okay, this one, if you look at what's happening to it, and as it continues, you know, thinking of an upside down parabola, this would be the second. What would the second derivative of g of x be? Well, it would be equal to negative, because negative things happen to you, it makes you want to frown. So that's just, you know, so it's concave down. So we defined this kind of a shape, this and this, as concave down, and this one here, or this one there, those are both concave up. So they kind of, you know, concavity, like a contact lens, or if you wear glasses, everything has a concavity to it. Okay. Well, what it's going to allow us to do is, if we do what we call a second derivative test, we take the second derivative, and we find in that area, is the second derivative positive or is it negative? It will tell us whether we have a maximum. A negative second derivative means we would have a maximum at that point. A positive second derivative tells us we have a minimum at that point. And again, we have the tools of graphing calculators, so we actually could just graph it and we could see. But these tools, again, back in the 80s when I was learning all of this, we didn't have the ability to just graph things quickly, so we had to understand these rules to determine whether it was a minimum or a maximum. Okay, so we're going to look at a couple examples. What they're going to do is they're going to give you a function. They're going to ask you to find the critical values. That's everywhere the first derivative is 0. And then they're going to ask you to identify whether those derivatives, those are maximums or minimums. And you can graph it and you'll see it, but the other way to do it is the second derivative. Take the second derivative. If the second derivative is positive there, positive, we're going to have a minimum. If it's negative, we're going to have a maximum. So we'll go through one of those examples, but that's all we're using it for, is to kind of build off of this concept. So yeah, they say the derivative of f of x on that graph, it's increasing, it's becoming steeper and steeper, so the rate of change is increasing. G of x, if we take its derivative, we see that that's decreasing, so the second derivative is negative. So it's just the words behind everything we said on the other page. Here's, again, more formal definition. Concave up means it holds water, is what we used to say. It's like a wine goblet up. Concave down means you turn the wine goblet upside down and it spills the water. So those are the two things. And one other thing I didn't talk about, but when you change concavity, so if you go from concave down to concave up, somewhere in the middle, you've got to have what's called an inflection point. That's the place where the concavity changes, right? You can't go from, you can't go from being a positive value to a negative value without passing through 0, unless you're not constant. So point of inflection will be the place where they change concavity. And, oops, I'm not doing a good job there. But we'll see it graphically. It's also going to be the place. So if concave down is a negative second derivative, concave up is a positive second derivative, what do you think happens at the point of inflection? It's got to be 0. It's got to be between positive and negative, and that's exactly that's how we can find it. Where the second derivative is 0 is typically going to be an inflection point. Not always, but it's a good guess. Okay, so locating points of inflection, that's exactly what it says. Find where that second derivative is 0. They can also exist where the second derivative is not defined, but most of the ones we're going to be looking at, they're continuous, and it'll be where the second derivative is equal to 0. So graphically, what they look like, we're going from concave down here to concave up here. So somewhere in between, you're going to see you're going to kind of be able to eyeball it on these graphs. They will give you a few graphs, and you'll be able to do that. If they give you the function, you take the derivative, the derivative of the derivative. Again, we got the second derivative, set it equal to 0, and that's going to give you those points of inflection, right? And again, it's just what we said. Concave down, second derivative is less than 0. Concave up is greater than 0. How can you go from being negative to positive? You got to pass through 0 someplace, and that's the inflection point. Thing of the inflection point is it will be the place of quickest change, either quickest negative change or quickest positive change. So it's where the rate is really at this fastest. So sometimes we want that inflection point because that's where change is going to happen the fastest. Okay, so let's go through this second derivative test. We can perform the second derivative test to find where something is either concave down. So when the second derivative is less than 0, we know it's concave down. So that's going to give us a max. If we get the second derivative and it's greater than 0, it's positive. That means we have a relative minimum. Okay, so we're going to look at some examples. But that's if we look at the graph, we can just see it, right? But if we don't have access to the graph, we take the derivative and the second derivative and get there. Okay. So this is basically the test right here. If the second derivative is positive, if it's greater than 0, that means we have a relative minimum. Just think of a smile has a low point there. If the second derivative is less than 0, that means it's negative. That means we've got this frown. That means we've got a high point. That gives us a maximum. Okay. It's kind of backwards how I would think of things. I would think a maximum is positive, but it's the other way around. So let's look at an example here. So again, taken right out of the homework, find the x-coordinates of all the critical points. Again, what is a critical point? It's a place where the first derivative is 0. So we first got to find those. And then we're going to use the second derivative test to get there. Okay, so first thing is to take the first derivative. So what's the derivative of g of x? The 3 comes down. We get 3x squared. Derivative of negative 3x is going to be negative 3. Derivative of 7 is 0. So there's our first derivative. We want to find the critical points. So critical points are where this first derivative equals 0. Okay, and remember those are going to give us either maximums or minimums. So I take 3x squared minus 3 equals 0. We could add 3 to both sides. 3x squared equals 3. Divide both sides by 3. X squared, oops, not x squared, not x cubed, x squared, sloppy. X squared equals 1. Take the square root of both sides. And remember, when you take the square root of both sides, you get a plus or minus. So really it's saying x is equal to positive 1 or x is equal to negative 1. So we've got two places where we could get a 0. And just think, if you plug in positive 1 and square it, you get 1. You plug negative 1, square it, you get 1. So we've got two places where the original function has a positive, or where the first derivative is 0. So we know we have either a minimum or maximum at these points. Um, and again, what we would do is we could plug it into here and figure out which one was bigger or smaller. We could look at the graph, or we could take the second derivative, and then we'll plug in each value and we'll see if the second derivative is positive or negative. And then we'll tell from there. So second derivative is going to be what? 2 times 3, 6, x to the first power, derivative of negative 3 is 0. So that's what our function is. What do we get as the sign, when we plug in, let's start with negative 1. So I'm going to take both of these values, right? I'm going to plug in negative 1. That's 6 times negative 1. That's negative 6. Is that positive or negative? Well, it's negative, right? What does negative mean? Negative means we have a frown, so do we have a minimum or a maximum? Minimum. Good. So we got a minimum down here at the critical point x equals, and they want the smaller x value, so this is where we're going to put negative 1. We're going to want to choose relative minimum for this one. And that's what the drop-down list gives you: relative min, relative max, or neither. And again, you could plug it in here. You could find the value it is as well. We want to plug in to the second derivative. We want to plug in the number 1. 6 times 1 equals 6. Is that positive or negative? Well, it's positive 6. So that means, wait, I did this backwards, didn't I? Anyone catch me on my, if it's negative, it makes you frown, right? Sorry, got to back up. I just realized it because I was going to go do this one. A negative makes you frown. Maybe that's why nobody was answering. Which gives us what kind of a point? A maximum. Okay. So that's going to give us a relative max for this one. We plug in 1, we get a positive. Positive is what makes you smile. And that means we're going to end up with a minimum because it's at the bottom. So at positive 1, we have a relative minimum. I hope I didn't confuse anyone too greatly. But when I drew a smile and I said I was frowning, hopefully you picked that up from the art. But you see, negatives make you frown, positives make you smile. That's the way, and then that's why you can know whether it's a min or a max there. Okay. You could also go back and graph this thing and you would see it very clearly as well. So I encourage you to use all of your senses in doing this. You know, so your intellectual working through this way, but also graph it so you can see it visually and see what happens. Okay, and I guess it would be something, you know, I think you'd see a graph that looks something like that. The maximum at negative 1, the minimum at positive 1. Is that okay? But there's a couple questions like this. They'll give you different functions there. You'll do the same thing. You'll take that first derivative, set it equal to 0, find those x values, take the second derivative, plug in those x values, and figure out whether they are a max or a min just from them. But remember, always you've got to back up, go ahead and graph them.
Since the middle is 2 point to 0, would that be the point of inflection?
Most likely. And if we take this derivative, yeah, because if you plug in 0 for x, you get that the second derivative is 0. That's one of the characteristics of the inflection point. Yes, so usually the inflection point is halfway between, and that's a good call. So visually you'll see it, and then you can analytically, where the second derivative is 0, that's generally going to be where your inflection point is. Thank you. How are we doing? Is it making sense? Getting boring already? Oops. Let's see if we're done yet. Oh, No more slides. I think we're done. Let me see. Let me make sure. Yeah, that's it. So, be looking over the weekend. I will come up with like a quiz. The idea is that you'll be able to work it multiple times. You'll be able to get all the points, but I'm going to do it in a way that either way you're going to learn how to approach the questions on the test. Okay? So that's the goal. I'll work on. I'm not exactly sure what it'll look like, but I'll get it into Canvas over the weekend so we can start getting ready for that test, because I'd like to see some really awesome scores for everybody. Makes it a lot easier for me.